Yes, all right. So today the speaker is Peter Burton, and he is going to talk about incompatibility of quantum games and Johnson-Lindenstrauss dimension reduction.
Okay, so yeah, thanks everyone for logging on. So to tell you a little bit about my title. So this phrase incomputability of quantum games refers to a recent result, which is widely considered to be a huge breakthrough. It's due to Thomas Vidic and a group of collaborators. And so this result that they proved shows that certain kinds of games which model quantum cryptography have no computable solution. So to just put a little bit more about what I mean by that, in the context of quantum cryptography, a game is something that has a numerical result, and computing this numerical result is as hard as the Halting problem. So that's the sort of just general idea of what I mean by incomputability of quantum games. So now I'll start trying to make that precise. So we want to define an object called a two-player non-local game. So first I'll define something a little bit more general. So we want to have finite sets X and Y. So these sets X and Y are supposed to represent questions, but on a mathematical level, you can just think of them as unstructured finite sets. And then we have two more finite sets. Okay, so again, these are supposed to be sets of answers, and the way we want to think of it is that A is a set of answers to the questions in question list X, and B is a set of answers to the questions in question list Y. But again, on a mathematical level, these are just unstructured finite sets. Then we have mu. So this is a probability measure on X times Y. So this mu is supposed to be a distribution of questions. I'll say a little bit about that in a moment. And then we also have what's called a decision procedure, which is just a function from this product to Boolean values. And so what this thing D is supposed to do is it's supposed to be saying that this D is some kind of verifier or impartial referee for the game. And what we're trying to do with the game is answer these questions correctly. And so if I have two questions and two answers, then D of this quadruple is supposed to be 1 if these are the right answers and 0 if these are the wrong answers. And so the key quantity associated with this construction is the, oops, I'm sorry. So the key quantity associated with this construction is the following. So, given given a probability measure P on X times Y times A times B, defined. So all this data is supposed to be a game. So we'll call this game G. And then we can evaluate the game at a probability measure. And what we're going to do is we're going to say that G of P is the sum over all X, Y, and A and B. So this is a sum over this, 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 and this. And then we're going to put mu of x, y. And then we're going to put the decision procedure. And then we're going to put these okay, so this is a positive number. You can see it's between 0 and 1. And so what this construction is supposed to communicate is the following. This probability measure P is a strategy for 2 players. So what this number means is you have 2 players, let's call them Alice and Bob, and A is supposed to be Alice's alphabet and B is supposed to be Bob's alphabet. And then this P, X, Y, A, B is supposed to be the probability that if we're asked, Alice is asked A, Bob is asked Y, they're going to answer Alice says A, Bob says Y. So this is the probability of giving a certain pair of answers when asked a certain pair of questions. And we want to think of this probability distribution as a kind of strategy. So Alice and Bob are trying to produce this strategy to maximize the value of the game. And what G of P is supposed to represent is it's given this kind of randomized strategy, what's the probability that you win the game? So the question of studying these games becomes interesting when you put certain restrictions on these probability measures. And
so Peter, P is actually not really a probability measure, but it's a family of probability measures.
Yes.
X by X and Y.
Yes, so, sorry, you're correct about that. Let me change the notation here. So what we should input to the game to evaluate it should be a family of probability measures like this, indexed by X and Y in X times Y. So maybe let's call this object P bar. So for each pair X and Y, we have a distribution on answers. So they ask us questions X and Y, and we have a certain distribution on answers. So instead of, this was a little incorrect. Instead of evaluating it at a single probability measure, we should evaluate it at a family of probability measures indexed by X and Y. And the idea is that the probability measure PXY is Alice and Bob's strategy to respond to the questions X and Y. So as I said, this becomes interesting when you put certain restrictions on these families of probability measures, but does this make sense on a just formal level of what this data means and how we get this number?
Just a quick question. So would G of P bar equals 1 mean they can always win or something?
Yeah, so G of P bar equals 1 would mean that they can win this game 100% of the time.
So is it an assumption that for every X and Y there is an A and B so that D gives 1?
No, certainly not. You can have a game which is impossible to win. So
okay.
D could be identically 0, and then
zero. Okay.
all the answers are just wrong. So that game would have that game would be impossible to win.
Okay. And mu is not known to is mu known to us?
Okay. Before I start interpreting this in the context of who knows what, that kind of interpretation only makes sense once we've restricted these probability measures. So let me tell you a little bit about how we want to restrict these probability measures, and then I'll be able to give the explanation about who knows what. So let me tell you what the relevant let me tell you what the relevant restrictions are. So the classical case, so the classical case is supposed to be when p x y equals px times py, or px in okay, so this restriction where we say, all right, each of these probability measures has to be a product of, you know, a measure on A and a measure on B. So this is what we would call the classical case, or this is what we would call a classical game. And so the classical value of the game, so let's say the classical value, maybe put C here for the classical value of G, equals, so this is the classical value of the game. It's like you can say a classical strategy is something which splits as a product of probability measures like this. And then the classical value of the game is what the best I can do with this kind of strategy. And so now that we have this picture, you can sort of see who knows what. So let's say this is a classical strategy, which is splitting as px of A and py of B. Okay, so all of this data is known to both Alice and Bob. So Alice and Bob know what X and Y are, they know what A and B are, they know what mu is, and they know what D is. So the point that they don't know is that they're not allowed to coordinate this strategy by having this be a function of B. So this is the kind of separation condition which puts a restriction on the strategy. The analysis of these games would be almost trivial if you allowed arbitrary probability measures here. So the point about this restriction is that you're not allowed to have the X answer also depend on B. So Alice and Bob have to decide a strategy, and then once they've decided on that strategy, they can't coordinate answers depending on each other's questions. They have to only answer based on the question that they saw. Okay, so the quantum case, we allow ourselves to use a wider variety of these families of probability measures. So there are many, many variations of this game, and I will say a particular one as the quantum case. If you want to be more precise, you would say this is like a spatially separated strategy or a tensor product strategy, but I'll just call this as the quantum case of the game. Okay, so in the quantum case of the game, so I'll just make a definition so people remember. P of M is a family of positive operators. Let's say this family is T J. So this is a family of positive operators such that Tj, tk is 0 when k is different from j, and the sum of these things is the identity operator. So this is supposed to be a generalization of the concept of a probability measure. It's kind of like a non-commutative probability measure where instead of taking positive numbers that sum to 1, you take these positive operators which have orthogonal ranges and sum to 1. So this is a positive operator valued measure. And so if we have a positive, so what we want to do for the quantum strategy is basically what we do is rather than putting conventional probability measures here, we allow us to construct strategies based on these positive operator valued measures. So what we're going to do is we're going to say that Alice has AX for X and X. And each one of these objects, AX, is a POVM, just like how PX is a probability measure. So this is a family of several operators, and the operators are going to be indexed by the questions. So AX is a POVM indexed by the questions, so, or the answers. So for each question, Alice has a POVM indexed by the answers. And similarly, Bob has a family of POVMs indexed by the answers. Okay, so then BY is going to be this family of operators indexed by the answers to Bob's question. And so what we want to do to get these numbers out of these objects is we're just allowed to say that, well, PXY of AB is supposed to be psi of AB. Okay, so this is how we're allowing ourselves to generalize the family of probability measures that are permissible for use in this game. We're doing kind of a non-commutative version of the classical case, and the key observation is that if this, so this is supposed to be a unit vector psi, and then we have these families of operators that are producing our probability measures. And if we force psi to split as a tensor product, then we would really be getting nothing more than the classical case. But since we're allowing psi to be an arbitrary unit vector, this is a much more powerful way to construct strategies than the classical case.
Quick question. So I remember, you know, Lewis was explaining this, and maybe you also, Peter, last semester. We're meant to think of psi as some sort of quantum device or something. Is that right?
Yeah. So the way you're supposed to think about this kind of strategy is sort of like the following. It's like, well, this psi is like some kind of particle that, so in the classical case, it's like Alice observes the world in her location, Bob observes the world in his location, and there's no relationship between these locations, right? But the point here is because this state psi is somehow like an entangled particle or something. The idea is supposed to be that in the quantum case, as part of their strategy, Alice and Bob are allowed to exploit the phenomena of quantum entanglement to get around spatial restrictions. And so, you know, psi is like some particle that's entangled between them, and the tensor product here is indicating that they're still measuring it in a spatially separated way. So Alice is over here and Bob's over here, but what they're observing is somehow entangled between the two locations. Tensor products, and you know, this is maybe a simpler version of a tensor product, are kind of a mathematical formalization of spatial distance. It's like when you split a Hilbert space as a tensor product, that's like putting two observers in remote locations.
Okay.
Okay, and then I'll write val star here for this quantum strategy. And I'll just say for this quantum case, we can allow ourselves, there's no loss of generality if we restrict to finite dimensional spaces. So in this quantum case, we can think of A and B and psi as all living in a finite dimensional space, and there's no, you don't get any more strategies by allowing these things to live in infinite dimensional spaces, assuming that you have the tensor product. And so this result that I was talking about due to Vidic and collaborators is that this sorry?
Excuse me? Sorry. I think you meant that the star value is the same, but there are more, like the set of quantum spatial correlations is larger than the quantum correlations, like the finite dimensional is smaller.
Oh, yes, I see what you're saying. Yes, you're correct. This value is the same regardless of whether you allow yourself to use infinite dimensional spaces, but there is some difference in what numbers you can actually get. It's just that they all work out to the same value for the game. So this number is what Vidic and collaborators established to be uncomputable. So more specifically, they said that, okay, let's say you have a quantum game presented as just this list of finite data I had before, and then you want some oracle promises you that the value of this game is either less than or equal to 1/2 or equal to 1. And your task is just to figure out, given so your task is to compute from the initial data of the game whether this value is less equal 1/2 or equal to 1, promised that one of these is the case. And the result is that this is as hard as the halting problem. Okay.
And
so,
sorry, again, I missed what you said a minute ago. The distinguishing between finite dimensional and infinite dimensional Hilbert spaces, what difference does that make again?
So if you allow these to be infinite dimensional, you get a larger family of possible strategies, but those extra strategies don't really help you. You can't use those additional infinite dimensional strategies to raise the value of the game. So the value of the game is already achieved as a supremum of finite dimensional strategies, and even though there are infinite dimensional ones, they're just not helping you for this number.
Okay.
Okay, so what I want to do in the rest of the talk is sort of describe this result we proved, which kind of really, I think, picks apart this incomputability phenomenon into kind of its DNA. So let me try and express this. So the reason that this problem is formulated in this way is for physical reasons. As I've described, there's physical interpretations to a number of aspects of this setup. But there are much more elementary mathematical incomputabilities which can be derived from this setup, and that's what I want to show you. So let's say that so we have all of these strategies, and what we can do is we can ask, well, I'm trying to figure out the value of this game, but when A and B are fixed, all of these possible strategies are just kind of members of a certain compact set. They're just, vectors in the unit ball of some c to the n for an appropriate n. And therefore, if we're trying to solve this problem of whether the game is value 1 or less than a half, in order to do that, all we have to do is be able to recognize whether a vector in this appropriate unit ball actually came from one of these strategies. So it's what you could call a membership problem or a kind of recognition problem. So the point is you just have some V in, well, here it's only even going to be 0, 1. So it'd be 0, 1 to the x times y times a times b. So there are more restrictions, obviously, but any strategy like this we can just think is an element of this space. And so for the purposes of computation, all of this data is given to us, and we're allowed to perform an exhaustive search through this cube. And so since we're only trying to get the value of the game right up to a half, we can sort of look through mu and d, which we know about, and find some positive epsilon, where all I have to do is recognize where a vector in here is within epsilon of something you can achieve like this. So that's what, so if you think about it, if I were able to determine which vectors in here are within epsilon of these strategies, then I could, if I could do that in a computable way, I could just exhaustively search through this cube, and each time I find something which is in epsilon of a strategy, I plug it into here, and I check what it comes out to be. And this is only a bounded thing, and I have a positive epsilon, and eventually I'm just going to look at all the possible strategies, and I'll figure out what the value of the game is, assuming I only have to do it with this gap of a half. So the problem of recognizing which vectors in this space are within epsilon of these strategies is kind of transparently incomputable, because doing this would give a way to compute these values. And now I'm going to try and I'm going to sort of skip over a bunch of details and just tell you that recognizing these strategies can be converted into a problem of recognizing a recognition problem which is somehow simpler. So let me make some definitions here. So we can say quantum correlation matrix of type ND is N by N matrix Okay, so quantum correlation matrix is what we're going to, of type ND, is what we're going to use to refer to a matrix with this form. So you have a list of n d by d unitaries, and you're doing this thing where you're taking the normalized trace of these products. And just to think about what's going on here. So that trace is just the dot product of the columns. So if I have like, I don't know, 3 by 3 unitaries, I could write them out as 9-dimensional vectors like this, and then the product would just be 1/3 of the dot product of these two vectors. So what we're doing here is, you know, a correlation matrix is just a matrix of inner products between vectors, and we're specifying a special type of correlation matrix, which comes from vectors that are structured like this, where you have segmentation into orthonormal components. So this is a special kind of correlation matrix, which comes from unitaries, or on kind of a more elementary level, which just comes from vectors that have this orthonormal segmented structure. And the reason I'm introducing this class of matrices is because the problem of recognizing which vectors in here came from POVM strategies can be converted in a relatively standard way to the problem of recognizing which matrices are quantum correlation matrices. So if we say, let's say that we say this is Q, C, M, N, D. So then we can say, all right, we can look at the and we'll call this QCM N. And so again, these are just n by n correlation matrices, and this condition requires that there are all ones on the diagonal. So these are elements of a compact set in n by n, c to the n by n. And so we have, again, the same type of problem where we're trying to recognize whether an n by n matrix is within epsilon of this set. And what I want to tell you is that, as I said, there's a relatively standard way to exchange the recognition problem for the set of POVM strategies that was preventing us from computing these games to these quantum correlation matrices. And so it's also incomputable given n and a matrix n by n matrix to recognize whether it's within epsilon of this set. Okay, but let's really try and think, well, what's going on here?
Sorry,
So,
Peter, can I ask one thing? That just seems kind of hard to believe. So you're saying take all, fix n, or you allow n, is the reason because you have to consider all n? If I fix
so the question is this, right? Give me n, give me an n by n matrix and a positive number. I want to tell you whether it's within this set. So in terms of computability, if you fix n, there's a stupid answer to the computability question, which is just, I could, if n is 1,000, I could compute this by just feeding my program enough data to recognize this where n is 1,000 for that particular thing. So in order to get a proper incomputability statement, I need to allow n to go to infinity in order to avoid this situation where I can just throw in a finite amount of initial data to specify QCM 1,000 or something like that.
Right, okay. Okay, so the precise question that's not computable is if you, sorry, you're given
let me say it in the most precise way possible. So here, okay. So
also, there was a question in the chat too, which we should not ignore too.
What if D is fixed? Well, you're asking what if D is fixed and n is going to infinity?
Yes.
So I don't really know anything about that regime. I've only, in the context of this problem, I've only ever thought about the regime where n is fixed and D is going to infinity.
Okay, thank you.
Yeah, so let me try and make this problem as precise as possible with discrete things. So give me an n by n, we can say rational matrix and some, positive epsilon. And then what I'm going to say is, again, an oracle is promising me that this matrix is either in this set or it's epsilon far away from this set. And I'm just supposed to tell you which of one of those possibilities is actually the case. And the rationality of this matrix is washed away by the small error. So, we're not, I said rational just to give you an idea of how this is properly discretized, but the small error, that means the rationality is not really restricting.
But I'm sorry, I'm still confused. If you hand me an n by n rational matrix and an epsilon, I think what you said a minute ago is I can just brute force compute all the, start to sample all of QCM n, since n is now fixed, and decide. Can
so
I
what the point is, so if I have this data, then sure, so let's call this matrix A. So if A is in QCM n, well, let me say it like this. For all n, there exists D. So QCM n is epsilon contained in QCM D, or ND. So you're correct that if I give you n, there is some d where if I could just check up to dimension d, then I would brute force exhaust QCM n. But the point is, you can't compute this d from this n. So if you have this rational n by n matrix, there is some dimension where, sure, if I checked up to that dimension, then I would find all of these things in QCM and I would be able to answer the problem. The issue is I can't ever figure out how high I need to check in order to get this to happen.
I see. Okay, I had misunderstood. Okay, so it becomes dense, but you don't know how fast or something.
Yeah, exactly. As d goes to infinity, this becomes dense, but you can't figure out how high you need to go to achieve epsilon density.
Okay, thank you. Thank you.
Okay, so now with what you see here, you can see how this is kind of a dimension reduction problem. What we're asking is, well, I have these data, which we can think of as inner products between these vectors, like I was saying before. And then we're saying, well, I know that I can reduce whatever I start with. There is this d where I can reduce the dimension to d. But there's no way that I can replicate these. There's no way that I can replicate all of these possible arrangements of inner products in a dimension that's computable from n. So, if you think of arbitrary correlation matrices, they're just, positive definite matrices. So matrices with self-adjoint matrices with non-negative eigenvalues. And so it's certainly easy to do this dimension reduction for arbitrary correlation matrices. So if I have a correlation matrix, let's say, call it C, so I can unitarily diagonalize this thing C, and because it's positive, all of the things here will be positive. Maybe it's, well, put this over here just to be a little more useful. And so then I can look at square root d u. So I look at the columns of square root du, and if this is an n by n correlation matrix, this is a list of n-dimensional vectors which exactly achieve this correlation matrix. So if you are trying to replicate, if you're trying to do dimension reduction for correlation matrices without this quantum restriction, you can say, look, I have these inner products which were generated by vectors in some gigantic space, but I can just forget about this gigantic space where the vectors were originally living, and I can just do this elementary construction, and then I'm going to get the same correlations with a computable dimension, which is, so here the dimension is n, right? It's d equals n if you're not putting a quantum restriction on this problem, because you can reduce an n by n correlation matrix to correlations between vectors of length n. But the issue is, if C starts out being unitary, there's absolutely no reason why these columns should be, if C is a quantum correlation matrix, so if C came from this construction with unitaries, we can do this, but there's no reason it's going to give us another quantum correlation matrix. There's no reason that this thing should, again, be representing the correlations between unitaries. So you can see what we have here is kind of a quantitative gap in dimension reduction. So if you're allowing arbitrary correlation matrices and not putting any quantum restrictions, you can do dimension reduction as well as possible. You can just do it all the way down to the dimension of the correlation matrix. But if you impose this condition in its full strength, then you have this completely incomputable form where once you ask about quantum correlation matrices, there's just nothing there's no construction that's going to help you to do this dimension reduction and solve the problem. And so in the last few minutes here, I want to talk about our result, which kind of interpolates the gap between these things. So what I want to do is I want to say, so we're going to say, let K be a function from natural numbers to natural numbers. So we can say it's non-decreasing, and K of n is less than or equal to n. So then we can do the following. So we can say we're going to define a set, maybe let's call it intermediate correlation matrices of type n, d, and then this is going to depend on this thing k. And so what we're going to do with these intermediate correlation matrices is we're going to say this is the set of matrices Okay, so this is how I want to kind of address the gap between these two dimension reduction problems. So the point I'm trying to make here is, let me redraw this picture I had before with the inner products for unitaries. So it's like, well, in the vector case, I'm just taking dot products between two vectors. And in that case, the problem has this elementary, the dimension reduction has this wonderful solution where you can reduce the dimension as much as humanly possible. And then the full quantum unitary case is where you're forcing yourself to live with these highly structured vectors that split up into complete orthonormal bases. And then the point about these intermediate correlation matrices is that you have some kind of intermediate restriction where you're saying, all right, I'm trying to take correlations between these vectors, but I'm not forcing myself to stack n orthonormal ones on top of each other. You know, here I'm only forcing myself to put one vector and the orthonormality constraint doesn't even appear. And then here you're saying, okay, these things have length n, and I'm forcing myself to stack kn of them on the end of each other and remain orthonormal. And then I'm asking, well, what kind of correlations can I get from this kind of intermediate restriction? And so the theorem I want to present here is that this problem being hard is really very it's absolutely about the whole orthonormal basis. It's not hard if this is any kind of looser restriction. And so to put this more precisely, so we can say if, so if Kn is little o of n, so then, well, so let me see if no, oh, my notation's all screwed up here. I keep using n for d, so let me just replace n with d everywhere. The point is this, well, no, okay, sorry, forget what I said. I was correct using n. So we have this function k, and we're trying to recognize whether n by n matrices are produced from this construction where you have an intermediate orthogonality constraint. And the point is, this is computably recognizable. And we can even say, so that for this problem, we can take D to be, so yeah, for this problem, we can take D to be a large constant depending on epsilon times an explicit polynomial in n. So, you know, this is a computable constant depending on epsilon, and then there's some explicit polynomial of n, which tells you how high you have to look depending on, how high you have to look to be able to recognize these restrictions with an intermediate orthogonality constraint. So the point is, in order to make this problem hard, you really need to enforce pretty much the entire orthogonality constraint to make these a complete orthonormal basis rather than some sort of weaker orthogonality constraint. Okay, so that's the end of the material I wanted to present. I'll open it up for questions.
Hey, Peter, maybe could you just explain that last part again? I'm a little confused about the subtlety. You're saying if I'm making correlation matrices using, you know, n d-dimensional operators, then I can't tell if a matrix is close to one of those. But
so if they're unitary, well, it depends what kind of operators there are. If they're actually unitary, then you can't tell, right? But if they're slightly weaker than unitary in the sense of they have a whole number of orthonormal columns, but it's not square, right? So you have like a bunch of orthonormal columns, but they don't fill out all the way to the square and get you a complete orthonormal basis. So it's like, in order to make this problem hard, you need to be forcing these to be actually unitary operators. If you allow them to be a little bit thinner with orthonormal columns, then the problem immediately becomes computable. And you know, you can do this dimension reduction in a pretty explicit way as soon as these are just a tiny bit thinner than unitaries.
Okay, so you're saying so for some explicitly computable d, which is some polynomial function of n, you know how big of a dimension you need to go to you know, to
Yeah,
become
exactly.
dense in QC in this.
Yeah, exactly. So you know, with the vectors we had d equals n, right? And then with the full orthonormal bases, we had like d is some crazy incomputable function. And the point is, if you have anything which is smaller than n, then that's already computable. The incomputability is coming from enforcing pretty much the complete, forcing these matrices to be really fat, right? So we can think of vectors as kind of very thin matrices with no orthonormal constraint, and then as we fatten them, it gets harder and harder to solve the problem because you're putting more and more of a constraint on yourself with how many orthonormal things you need to separate out there. And then it's like, well, in order to make this hard, you really need pretty much the entire orthonormal basis.
Interesting. Thank you.
This whole thing seems to have a lot of the flavor of all the MIP star stuff we were talking about in the spring, but it doesn't seem to be quite the same. Can you just say something about how it is and isn't related?
So do you want me to start from this stuff or more go back to like the quantum games and talk about how that's related?
Either way. I'm just seeing a lot of stuff that seems familiar, but in a, yeah, I've sort of seen this before, but not quite.
Yeah.
And then other stuff that it's like, no, I don't think I've seen that before, and it's a little blurry about, you know, what part of your talk should I say, oh yeah, that's what we've done before, only with a slight twist, and what part is, and now for something completely different.
Sure. Yeah. So obviously the problem of reducing so the problem of dimension reduction for vectors has been extensively studied in many contexts because it's mathematically interesting and it's also actually useful for machine learning. So there are hundreds of papers about how to efficiently do dimension reduction for vectors. In particular, the keywords there are Johnson-Lindenstrauss, and this result is proved using a kind of more advanced, well, it's kind of like, it's how these things always go, which is you have to do some appropriate preconditioning process and then take a kind of randomized projection. But so I would say, you know, this result is in the family of dimension reduction results as an example of as far as you can possibly push these things, right? So this is like as far as you can push dimension reduction without running up against this somehow just impossible dimension reduction problem. So, you know, the point about Johnson, let me give you an example of how dimension reduction could work. Well, okay, so this is like a pushing dimension reduction as far as possible result, and it was motivated by learning that this kind of dimension reduction is impossible. So this dimension reduction being impossible is directly a consequence of MIP star, and I don't know that anyone ever studied this kind of dimension reduction with an orthogonality constraint outside of being motivated by MIP star. But I guess this result is supposed to say, well, in the context of dimension reduction with orthogonality constraints, you can solve the problem by pushing existing techniques as far as possible until you get right up to the case where k is a constant fraction of n. And then you run into this incomputability issue, which is coming from some very deep other place that, you know, I'm just like, well, this is impossible, but, you know, I pushed my techniques as far as I can to make it possible, and, well, it all makes sense. You know, I can push them right up to the point where this, whatever phenomenon is happening with these things kicks in, and then dimension reduction is just impossible.
Okay, so in other words, we're just sort of saying is if you're talking about a sparse problem, lots of new stuff. MIP star isn't all that relevant.
Yeah. So
If you're talking about the dense stuff, you hit a brick wall with a big sign saying MIP star on it.
yes, exactly. So, and
Okay.
this theorem is supposed to tell you exactly where that brick wall is, right? So you can do dimension reduction for as much as you want, and then the brick wall comes where the matrices are now fat enough that they're a constant rectangle, right? They're,
Right.
you know, the width is a constant fraction of the height, and then you just see MIP star, and this is impossible. But if it's anything less than that, you're on the right side of the brick wall.
Got it. Got it. Thank you.
So any other questions? There's something in the chat. Nice talk, Peter. Thanks. Yeah, thanks.
More questions? So I guess
Yeah, thanks everybody.
I guess I'll end the meeting now. Thank you, Peter, for your talk. Thanks.
Thank you.
Thanks.